Let's begin with absolute maximum. Let f be a function defined over an interval I, and let the point C an element of this interval I. We say f has an absolute maximum on I at C if f of C is greater than or equal to f of x for all x an element of I. Here we have a graph. The function is f of x equals 1 over x squared plus 1 on the interval negative infinity to positive infinity. We say that there is absolute maximum of 1 at x equals 0. This is the point corresponding to the absolute maximum. This is the highest point of the graph. Here is the second graph. The function is f of x equals cosine x on the interval negative infinity to positive infinity. We say that there is absolute maximum of one value at x equals 0, comma, plus or minus 2 pi, comma, plus or minus 4 pi, comma, and so on. These are the points corresponding to absolute maximum. These are the highest points of the graph. Here we have another example. The function is f of x equals x cubed on the interval negative infinity to positive infinity. In this case, we say that there is no absolute maximum. This part of the graph will go up continuously up to infinity. Now let us define absolute minimum. Let f be a function defined over an interval I, and let the point C an element of the interval I. We say f has an absolute minimum on the interval I at the point C if f of C is less than or equal to f of x for all x an element of I. Going to our previous example a while ago, the f of x equals 1 over x squared plus 1 on the interval negative infinity to positive infinity. We say that there is no absolute minimum. This part of the graph will continuously go down up to infinity. The same is true with this part of the graph. It will just go down up to infinity. So we say, again, there is no absolute minimum for this graph. The second example, the f of x equals cosine x on the interval negative infinity to positive infinity. We say that there is absolute minimum of negative 1 value at x equals plus or minus pi, comma, plus or minus 3 pi, comma, and so on. These are the points corresponding to absolute minimum. These are the lowest points of the graph. Another example is the function f of x equals x cubed on the interval negative infinity to positive infinity. We say that there is no absolute minimum for this graph. This part of the graph will continuously go down up to infinity. Next is absolute extremum. If f has an absolute maximum on I at the point C, or an absolute minimum on the interval I at the point C, we say f has an absolute extremum on the interval I at C. Take note, absolute extrema is the plural form of absolute extremum. Let us see some examples. Determine from the graph whether the function has any extreme values on the given interval. This is graph A. The function is y equals h of x. And this is the graph. Analyzing the graph, we say that the graph has an absolute maximum when x equals b. When x is equal to b, we can see that the graph has the highest point, and this is the point. This is the absolute maximum. Also, we say that the graph has absolute minimum when x equals c sub 2. This is the c sub 2. When x is equal to c sub 2, the graph is at its lowest point. This is the point. This is the absolute minimum. This is graph B. Our function is y equals f of x. This is the graph. Analyzing the graph, we say that the graph has absolute maximum when x is equal to c. This is the c. When x is equal to c, we can observe that the graph is at its highest point. And this is the point. This is the absolute maximum. Also, we say that the graph has absolute minimum when x is equal to b. This is the value b. When x is equal to b, we can observe that the graph is at its lowest point. This is the point. This is the absolute minimum. Graph C, our function is y equals g of x. Analyzing this graph, we say that graph has absolute maximum when x is equal to c. This is the c. When x is equal to c, we can observe that the graph is at its highest point. This is the point. This is the absolute maximum. Next, we can say that the graph has absolute minimum when x is equal to a. This is the a. When x is equal to a, we can observe that the graph is at its lowest point. This is the point. This is the absolute minimum. Let's begin with local maximum. A function f has a local maximum at the point C. If there exists an open interval I containing C, such that I is contained in the domain of f and f of C is greater than or equal to f of x, for all x an element of I. Now let us define local minimum. A function f has a local minimum at the point C. If there exists an open interval I containing C, such that I is contained in the domain of f, and f of C is less than or equal to f of x for all x an element of I. Now let us define local extremum. A function f has a local extremum at the point C. If f has a local maximum at C, or f has a local minimum at C. Note that the term local extrema is the plural form of local extremum. To illustrate, we have our graph here in blue color, and this is y equals f of x. Take note that some points of the graph are identified with some values of x, namely a, c, e, d, and b. On this graph, we say that there are two local maximum, and these are the points when x is equal to c and d. In here, we say that this is local maximum because there is no greater value of f nearby. And when x is equal to d, this point here is also called absolute maximum. We say that there is no greater value of f anywhere, or this is the highest point of the graph. Next, there are 3 points of local minimum, and these are the points when x is equal to a, to e, and to b. We consider this point as local minimum because we say that there is no smaller value of f nearby. The same is true with this point in here. But the point when x is equal to a, this point here is also called absolute minimum. We say that there is no smaller value of f anywhere. Or simply said, this is the lowest point of the graph in the interval. Now let us define critical points. Let C be an interior point in the domain of f. We say that C is a critical point of f if letter A, f prime of C is equal to 0, or letter B, f prime of C is undefined. Let us see example 1. Find the critical points of the function y equals 4x cubed minus 3x. For our solution, let us do the step 1, and that is to find the derivative. The derivative of this function now is y prime equals 12x squared minus 3. Step 2, we set y prime equals 0 and solve for x. So the y prime here becomes 0 equals the right side values. Let's solve for x now by first transposing this negative 3 to the left side. The negative becomes positive 3. And in here, we simplify this equation by dividing by 3. So the left hand becomes 1 is equal to 4x squared. Let us isolate the x squared by dividing this equation by its coefficient. Divide by 4. So we have now 1 over 4 is equal to x squared. This time, let us take the square root of both sides. So we have now x is equal to plus or minus the square root of 1 over 4. And we can simplify this into 1/2. So the value of x is equal to plus or minus 1/2. These are the critical points. Example 2. Find the critical points of the function f of x is equal to x squared over the quantity x minus 1, given that x is not equal to 1. For our solution, let us do step 1 to find the derivative. We can see here that our function is a quotient, so we will apply the quotient rule. So the derivative will be f prime of x is equal to x minus 1 times the quantity 2x minus x squared times the quantity 1 all over the square of the binomial x minus 1. Simplifying the numerator, we will have now 2x squared minus 2x minus x squared all over this same denominator. We can combine the 2x squared and the negative x squared. So our derivative now becomes x squared minus 2x all over this same denominator. This is now the derivative. Step 2, we set y prime or the derivative equals 0 and solve for x. So this f prime of x becomes 0, and let us rewrite our derivative here by factoring the numerator. So we have now x times the quantity x minus 2 over our same denominator. Let us now solve for x. Let us cross multiply the denominator to the left side. So this will be simplified into 0 equals the numerator itself, x times the quantity x minus 2. Now, let us equate each of the factors into 0. So we have this x equals 0 and the x minus 2 equals 0. We found the first value of x. This is the first critical point, x equals 0. And the second critical point, we transpose this negative 2 to the right side. We have now x is equal to 2. This is another critical point. So in here, we have 2 critical points. We take note that in our derivative here, we can see that the derivative is undefined when x is equal to 1. But since x equals 1 is out of the domain, you can see in here from the very beginning of the problem. So it is no longer considered as critical point. So on this problem, we have only 2 critical points, and those are x equals 0 and x equals 2. These are the final answers. Example 3. Find the critical points of the function f of x equals 3x raised to 4 plus 4x cubed minus 12x squared plus 2. Step 1. Let us find the derivative. So f prime of x equals derivative of 3x power 4 becomes 12x power 3 plus derivative of 4x cubed becomes 12x power 2 minus derivative of negative 12x squared is negative 24x. Derivative of plus 2 is 0. We don't write here. Then step 2. We set the derivative equals 0 and solve for x. So the trinomial equals 0. Then let us solve by factoring. This trinomial has a common factor, and that is the 12x, and to be multiplied by the trinomial, and that is x squared plus x minus 2. Then this trinomial can still be factored out. We have x plus 2 times x minus 1. we simply copy the 12x down here. We have here 3 factors for the trinomial. So we're going to equate each factor to 0 and solve for x. So we have here the 12x equals 0, x plus 2 equals 0, and x minus 1 equals 0. Let us solve for x respectively. For this 12x equals 0, we divide this equation by 12. So the 12 cancels out, equals the right side is 0 over 12. This is the first critical point. For the x plus 2 equals 0, we transpose positive 2 to the right. So we have x equals negative 2. This is the second critical point. Third, the x minus 1, this negative 1, we transpose to the right. So we have positive 1. X equals 1. The third critical point. So these are the critical points. Let us study this theorem. Let f be a continuous function over a closed, bounded interval I. The absolute maximum of f over I and the absolute minimum of f over I must occur at endpoints of I, or at critical points of f in I. Now, let us see how to locate absolute extrema over a closed interval. Given a continuous function f defined over the closed interval from a to b. Step 1. Evaluate the function f at the endpoints x equals a and x equals b. Step 2. Find all critical points of the function f that lie over the interval from a to b, and evaluate the function f at those critical points. Step 3. Compare all values found in steps 1 and 2. The largest of these values is the absolute maximum of f. The smallest of these values is the absolute minimum of f. Example 1. Find the absolute extrema. That means the absolute maximum and the absolute minimum of the function y equals negative x squared plus 3x minus 2 over the interval from 1 to 3. For our solution, let us do step 1, and that is to evaluate the function f at the endpoints. The endpoints are the end numbers of the interval, and these are the 1 and 3. Let us begin with f of 1. So we have here the negative of the quantity 1 squared plus 3 times 1 minus 2. This negative of the quantity 1 squared is simply minus 1 plus 3 times 1 is 3, then minus 2. Simplifying these three numbers, we have 0. The f of 1 equals 0. Then f of 3. And this is equal to the negative of the number 3 squared plus 3 times 3 minus 2. The negative of 3 squared is negative 9 plus the 3 times 3 is 9, then minus 2. Simplifying these three numbers here, the answer is negative 2. So f of 3 is negative 2. Step 2. Find all critical points of the function f that lie over the interval from a to b, and evaluate f at those critical points. Looking for the critical points, first we will take the derivative of the function. So we have now this y prime equals negative 2x plus 3. We can see here that our derivative is a polynomial function, so the derivative is defined in all its domain. Next, let us set the y prime into 0. So we have the 0 equals the right side members of the equation. Now let us solve for x. The positive 3 we will transpose to the left side. We have now this negative 3 equals negative 2x. Let us isolate x by dividing the equation by negative 2. So we have the left side to be negative 3 over negative 2 equals x. So the x here is equal to positive 3 over 2. So this is our critical point. Take note that this value is inside the interval from 1 to 3. Next, let us evaluate the function with respect to this critical point. So we have the f of 3 over 2. And this is now equal to the negative of the quantity square of 3 over 2 plus 3 times 3 over 2, then minus 2. Simplifying further, this expression here becomes the negative of 9 over 4 plus 9 over 2 minus 2. In the next step, let us show that we have equivalent fractions of same denominator. So we have this negative 9 over 4 plus the 9 over 2 becomes 18 over 4 minus the whole number 2 is now 8 over 4. Combining like fractions, we have now the final answer to be 1 over 4. So the f of 3 over 2 is equal to 1 over 4. Step 3. Compare all values found in steps 1 and 2. It's better if we can put a table like this. We have two columns. The first column is for the x, and this is the column for the endpoints and critical points. So we have the 1, the 3, and the 3 over 2. And the column above x, we will write the corresponding values. So we have 0, and this negative 2, and also the 1/4. Now, let us compare the values of the second column. Which one is the largest? Which one is the smallest? We can see here that the largest is the 1/4, and the smallest is the negative 2. So we write here that this 1/4 is the absolute maximum, and the negative 2 is the absolute minimum. In words, we can write like this: absolute maximum of 1/4 when x equals 3 over 2. Absolute minimum of negative 2 when x equals 3. This is our final answer. Example 2. Find the absolute extrema of the function f of x equals x squared minus 3x raised to 2 over 3 over the interval from 0 to 2. For our solution, let us write the step 1, and that is to evaluate the function f at the endpoints. Here are the endpoints. Let's begin with f of 0. And this is equal to 0 squared minus 3 times 0, raised to 2 over 3. Simplifying this, the value is equal to 0. So f of 0 equals 0. Next is f of 2. This is equal to 2 squared minus 3 times 2 raised to 2 over 3. Using the calculator, the answer here is negative 0.762. Step 2. Find all critical points of f that lie over the interval a to b and evaluate f at those critical points. First, let us take the derivative. The f prime of x is equal to 2x minus 3 times the fraction 2 over 3 times x raised to negative 1 over 3. We can cancel this 3 and the denominator 3. Simplifying further, our function now becomes 2x minus the fraction 2 all over x raised to positive 1 over 3. Let us combine them into a single fraction. So we have now this 2x raised to 4 over 3, then minus 2 all over x raised to 1 over 3. This is our derivative. Now let us set f prime of x into 0. So we have the 0 equals this fraction here. When the derivative is a fraction, we can get a value of derivative when it is equal to 0. Or we can take a derivative when it is undefined. So let us now solve for the x. Let us cross multiply this denominator to the left side, and this will just be 0. So we will have 0 equals this numerator. And solving for x, this negative 2, let us transpose to the left side, it becomes positive 2. From this line here, we can solve for x, and we will find out that the value of x is plus or minus 1. But take note that x equals negative 1 is out of the interval given in the problem. So we will only accept the value of x equals positive 1. Next, given that our derivative here is a fraction, there is critical point when derivative is undefined. It will happen if the denominator is equal to 0. So the x raised to 1 over 3 equals 0. And let us solve for x, so we will have x equals 0. In here, we have another critical point. But we say that the f of 0 was evaluated already in step 1. It means to say, we will only evaluate the critical point when x equals positive 1. So we have this f of 1 now equal to 1 squared minus 3 times 1 raised to 2 over 3. This 1 squared is 1 minus 3 times 1. This 3 times 1 is 3, and 1 minus 3 is simply negative 2. So f of 1 is negative 2. Step 3. Compare all values found in steps 1 and 2. We can put a table where the first column is x, and this is for the critical points and the endpoints. So we have here the 0, the 1, and the 2. And the second column is for the f of x. So we have 0, negative 2, negative 0.762 respectively. Now, let us compare the values in the f of x. Which one is the highest? Which one is the lowest? We can see here that the highest is 0 and the lowest is negative 2. So the conclusion is, we write here the absolute maximum and we write here the absolute minimum. In words, we may write absolute maximum of 0 when x equals 0. Absolute minimum of negative 2 when x equals 1. This is our final answer. Example 3. Find the absolute maximum and minimum values of f of x equals x squared minus 4x plus 3 over the interval from 1 to 4. Step 1. Let's evaluate the function at endpoints. It means our interval is from 1 to 4. Let us evaluate f of 1 and f of 4. Let's begin with f of 1. We have this function. Let us replace the x by 1. So we have now 1 squared minus 4 times 1 plus 3. 1 squared is 1. Negative 4 times 1 is negative 4. Then plus 3. Finally, the answer is 0. Then f of 4. We evaluate this function with 4. So we have 4 squared minus 4 times 4 plus 3. 4 squared is 16 minus 4 times 4, that is 16 also. Then plus 3. 16 minus 16 is 0 and plus 3 equals 3. Now step 2. Let us find critical points and evaluate the function at critical points. First, we take derivative of this function. Derivative of x squared is 2x. Derivative of negative 4x is negative 4. Derivative of plus 3 is 0. Then we let this f prime of x equals 0. So we change this value by 0 equals 2x minus 4. Let us solve for x. This negative 4 we transpose to the left side. From negative, it becomes positive 4. Then, we want the x. We divide this equation by the coefficient of x, which is 2. If we do that, we will get the value of x. X now equals 4 divided by 2, which is 2. So we have this x equals 2 as the critical point. In this problem, we have only one critical point. So let us evaluate the function using the critical point. So we have f of 2. Evaluating now, we have 2 squared minus 4 times 2 plus 3. 2 squared is 4 minus 4 times 2 is 8. Then plus 3. Finally, the answer is negative 1. Step 3. Let's compare all values found in steps 1 and 2. In the exam, we can do like this. When we say values here, we are referring to the numbers 0, 3, and negative 1. So, let us find the highest y value. We compare the three numbers. Obviously, the number 3 is the highest. So, we write absolute maximum equals 3. Now, we look for the absolute minimum. Let's go for the lowest y value. Again, we compare the three values, the 3, the 0, and the negative 1. Obviously, the lowest number is the negative 1. So we write absolute minimum equals negative 1. Hi everyone. Today we're going to study first derivative tests. Let us first define increasing function. If the derivative of a function is positive over an interval I, then the function is increasing over I. Here we have an example of a graph over the interval from A to B. This is the graph. On the graph, we can see two examples of tangent lines. This is the first tangent line, and this is the second tangent line. Both tangent lines are leaning to the right. It gives us idea that the slopes of the tangent lines are positive. Here is another example of a function over the interval from A to B. This is the graph. On the graph, we can see two examples of tangent lines. This is the first tangent line. This is the second tangent line. We can see that both tangent lines are leaning to the right. It gives us idea that the slopes of these tangent lines are positive. Now let us read the graphs from left to right. We can observe that the graphs are going upward. In this case, we can say that both functions are increasing over the interval from A to B. Also, the derivative of the function over the specified intervals are greater than 0, or we say positive. Let us define decreasing function. If the derivative of the function is negative over an interval I, then the function is decreasing over I. We have one example here of a graph over the interval from A to B. This is the graph. We can see here also two examples of tangent lines. This is the first tangent line, and this is the second tangent line. Both are dotted. We can observe that the tangent lines are leaning to the left. It gives us idea that the slopes of these tangent lines are negative. Here is another example of a function over the interval from A to B. This is the graph. On the graph, we can see two examples of tangent lines. This is the first tangent line. This is the second tangent line. We can observe that the tangent lines are leaning to the left. It gives us idea that the slopes of these tangent lines are negative. Now let us read the graphs from left to right. We can observe that the graphs are going downward. In this case, we say that both functions are decreasing over the interval from A to B. And we say also that the derivative of the function at this interval is less than 0. And that means the values are negative. To illustrate, let us see this function described by the graph. We say that this function f has 4 critical points, the A, B, C, and D respectively. Now, the function f has local maxima at point A and point D. At point A, we say that the f prime of A is undefined. In here, the tangent line is vertical. At point D, the f prime of D is equal to 0. We say also that there is a local minimum at the point B. Here is the point, and we say that f prime of B is equal to 0. Now, the function f does not have a local extremum at the point C, although f prime of c equals 0. This is not a local extremum for the reason that the sign of derivative changes at all local extrema. Let us examine the sign of derivative to these four critical points. Look at point A. This is the graph over A. On the left side of A, the graph is increasing. So we say that f prime is greater than 0 or positive. On the right side of A, the graph now decreases. And we say that the derivative is less than 0. So at point A, the left side is positive while the right side is negative. Now let us consider point B. On the left side of B, the graph is decreasing. While the right side of B, the graph is increasing or going up. So it means to say, on the left side of B, the graph is negative. While the right side of B, the derivative is positive. Let us consider the point C. On the left side of point C, the graph is increasing, and we say that the derivative is positive. While the right side of C, the graph is again increasing, and we know that the derivative is positive in here. So at point C, the sign of the derivatives remains the same. Look at point D. On the left side of D, the graph is increasing, so the derivative is positive. While the right side of D, the graph is decreasing or going down, so the derivative is less than 0 or negative. Let us study now the first derivative tests. Suppose that f is a continuous function over an interval I containing a critical point C. If f is differentiable over I, except possibly at point C, then f of C satisfies one of the following descriptions. Number 1, if the derivative changes sign from positive when x is less than c to negative when x is greater than c, then f of c is a local maximum of f. Number 2, if the derivative changes sign from negative when x is less than c to positive when x is greater than c, then f of c is a local minimum of f. Number 3, if the derivative has the same sign for x is less than c and x is greater than c, then f of c is neither a local maximum nor a local minimum of f. Here are the steps to find local extrema using first derivative tests. Consider a function f that is continuous over an interval I. Step 1. Find all critical points of the function f. Step 2. Divide the interval I into smaller intervals, using the critical points as endpoints. Step 3. Find f prime, or the derivative of the function. Step 4. Choose an arbitrary test point x in each of the sub-intervals of step 2. And evaluate f prime on those test points. If f prime is continuous over a given sub-interval, which is typically the case, then the sign of f prime in that sub-interval does not change, and therefore can be determined by choosing an arbitrary test point x in that sub-interval. The respective sign of f prime on a particular test point represents the sign of derivative in that particular sub-interval. Step 5. Use first derivative tests to determine whether the function f has a local maximum, a local minimum, or neither at each of the critical points. Let's see this example. Use the first derivative test to find the location of all local extrema for the function f of x equals x cubed minus 3x squared minus 9x minus 1. For our solution, let us do step 1, and that is to find all critical points of the function f. The first step is to find the derivative. So f prime of x is equal to 3x squared minus 6x minus 9. And from here, let us set f prime of x into 0. So we will change the left side into 0. So we have now 0 equals all the members of the right side. Then let us solve for x. Observe that the right side has a common factor, and that is the number 3. If we factor out that number 3, we will have 3 times the quantity x squared minus 2x minus 3. Let us simplify further by dividing this equation by 3. So the equation now becomes 0 equals x squared minus 2x minus 3. Then let us solve for x. We can solve this equation by factoring. So the factors are x minus 3 times x plus 1. And from here, let us equate each factor into 0. So the x minus 3 equals 0 and the x plus 1 equals 0. Solving for x in the first equation here, we transpose the negative 3 to the right. So x is equal to positive 3. And on the other equation, x plus 1 equals 0, the x value here now becomes negative 1. We can see here that we have two critical points when x is equal to 3 and x is equal to negative 1. Let us copy these critical points under step 1, just like we have here. Step 2 is to divide the interval I into smaller intervals using the critical points as endpoints. We are able to find the critical points. Now, let us plot them in the number line. Here is our number line. We write here negative 1, and on the right is the positive 3. We can see that our number line here is divided into 3 sub-intervals. The first interval is here, and we name this as from negative infinity to negative 1. Next interval is from negative 1 to positive 3. And the other interval here is from positive 3 up to positive infinity. Step 3 is to find the derivative. A while ago, we are able to find the derivative from step 1. So that is f prime of x equals 3x squared minus 6x minus 9. Step 4. Choose an arbitrary test point x in each of the sub-intervals of step 2 and evaluate f prime on those test points. We have 3 sub-intervals here. Let us choose arbitrary test point on each of the sub-interval. On the interval here, we can choose a -2, which is the first integer on the left side of -1. On the interval from -1 to +3, we know that 0 is part of this interval, so we can choose the number 0. On the third interval, we can choose the number 4. That is the first integer after number 3. Now, let us evaluate the f prime or the derivative on those test points. Let's start with this -2. So we have f prime of -2 is equal to 3 times the square of -2 minus 6 times -2 minus 9. The square of -2 is +4. 4 by 3 is equal to 12. -6 times -2 is +12. Then we copy the -9. When we simplify these numbers, the final answer is +15. We are more concerned on the sign of the number 15. So this positive represents the sign of the derivative on this interval. So we take a note here that we have a positive or the plus sign, and we know that we have an increasing function on this interval. Next is the f prime of 0. This is equal to 3 times 0 squared minus 6 times 0 minus 9. We can simplify this into -9. We are more concerned here about the sign of the 9. So this is negative. The negative sign represents the sign of the derivative in the whole sub-interval here. Let us take a note that we have a minus or negative sign, and we have a decreasing function over this sub-interval. Now let us evaluate f prime of 4. This is equal to 3 times 4 squared minus 6 times 4 minus 9. The square of 4 is 16. 16 times 3 is 48. -6 times 4 is -24, then minus 9. When we simplify this, the final answer is +15. Again, we are more concerned on the sign of this number 15, and that represents the sign of the derivative on this sub-interval. Let us take a note here of plus sign, and we know that there is an increasing function over this interval. Now, step 5. Use first derivative test to determine whether the function f has a local maximum, a local minimum, or neither at each of the critical points. Our first critical point is -1. The left side of the -1, the derivative is positive and it is increasing, while the right side of this -1 is negative. That is decreasing. So we say that at x equals -1, the sign changes from positive to negative. Thus, there is a local maximum at x equals -1. Next, the other critical point is 3. Observing the sign of the derivative on the left and right of this critical point 3, we say that at x equals 3, the sign of the derivative changes from negative to positive. So we say that there is local minimum at x equals 3. Using GeoGebra, this is the graph of our function here. We can see on the graph that there is a local maximum at x equals -1. This is the point. Also, there is a local minimum at x equals 3. This is the point. This is now our final answer. Hi everyone. Today we're going to study increasing or decreasing interval using first derivative tests. Let us first define increasing function. If the derivative of a function is positive over an interval I, then the function is increasing over I. Here we have an example of a graph over the interval from A to B. This is the graph. On the graph, we can see two examples of tangent lines. This is the first tangent line, and this is the second tangent line. Both tangent lines are leaning to the right. It gives us idea that the slopes of the tangent lines are positive. Here is another example of a function over the interval from A to B. This is the graph. On the graph, we can see two examples of tangent lines. This is the first tangent line. This is the second tangent line. We can see that both tangent lines are leaning to the right. It gives us idea that the slopes of these tangent lines are positive. Now let us read the graphs from left to right. We can observe that the graphs are going upward. In this case, we can say that both functions are increasing over the interval from A to B. Also, the derivative of the function over the specified intervals are greater than 0, or we say positive. Let us define decreasing function. If the derivative of the function is negative over an interval I, then the function is decreasing over I. We have one example here of a graph over the interval from A to B. This is the graph. We can see here also two examples of tangent lines. This is the first tangent line, and this is the second tangent line. Both are dotted. We can observe that the tangent lines are leaning to the left. It gives us idea that the slopes of these tangent lines are negative. Here is another example of a function over the interval from A to B. This is the graph. On the graph, we can see two examples of tangent lines. This is the first tangent line. This is the second tangent line. We can observe that the tangent lines are leaning to the left. It gives us idea that the slopes of these tangent lines are negative. Now let us read the graphs from left to right. We can observe that the graphs are going downward. In this case, we say that both functions are decreasing over the interval from A to B. And we say also that the derivative of the function at this interval is less than 0. and that means the values are negative. First condition, if f prime of x is more than 0, meaning derivative is positive value on an interval, then f or the function is increasing on that interval. Second condition, if f prime of x is less than 0, or we say that the derivative is negative on an interval, then the function is decreasing on that interval. Example 1. Use the first derivative test to find the intervals in which the function f of x equals 2x squared minus 8x plus 9 is increasing or decreasing. In here, we're going to follow 3 steps. Step 1, let us find the critical points. First thing to do, we take derivative of the given function. So we have f prime of x equals 4x minus 8. Then, we're going to let f prime of x equal 0. That means, from this equation, the left side becomes 0. Then we solve for x. Negative 8 we transpose to the left. The negative becomes positive 8. Then this is equal to 4x. Let's divide the equation by the coefficient of x, which is 4. Then x equals 2. In this problem, we have one critical point. Then step 2. Let us identify the intervals. Let us draw a number line and then we assume the location of the critical point. So here it is. Notice that in the number line, it is divided into 2 intervals, interval A and interval B. Let us write the corresponding interval notations for A and B respectively. For interval A, we have from negative infinity to 2. Interval B, from 2 going to positive infinity. Then step 3. We evaluate the derivative using a test point on each of the interval. Let's begin with interval A. Look at our interval A. Notice that the value 0 is in interval A. It is better to use that value for easy computation. Let us now evaluate f prime of the 0. This is our derivative function. So 4x minus 8 becomes 4 times 0 minus 8. 4 times 0 is simply 0, so the value is negative 8. Let's go to interval B. Look at our interval B here. Let us use the smallest integer for interval B, and that is the number 3. So let's evaluate f prime of 3. So our derivative function here becomes 4 times 3 minus 8. 4 times 3 is 12, minus 8 is positive 4. Now let us identify whether increasing or decreasing for an interval. Let's begin with interval A. The value is negative, so we say that it is decreasing on interval A. What about interval B? The value is positive, so we say that it is increasing on interval B. Example 2. Use the first derivative test to find the intervals in which the function f of x equals negative 2x cubed plus 6x squared minus 3 is increasing or decreasing. Step 1. Let's find the critical points. Let us take the derivative of this function. So f prime of x equals derivative of negative 2x cubed is negative 6x squared. Derivative of 6x squared is 12x. Derivative of minus 3 is 0. And from here, we let the f prime of x equal 0. So for this equation, left side becomes 0. So we have like this. Then let us solve for x. We can see that we can factor out the right side as negative 6x times x minus 2. Then let us equate both factors to 0. So one factor is negative 6x equals 0. The other factor is x minus 2 equals 0. Then let us isolate x. On the first factor equation, let us divide this equation by negative 6. So x equals 0. On the second factor equation, the negative 2 we transpose to the right. So x equals 2. On this problem, we have two critical points, 0 and 2. Then we go to step 2. Identify the intervals. Let's draw a number line and we assume the position of the two critical points. Make sure that the lower number is on the left side and the bigger number is on the right. Now observe that the number line is divided into three intervals, namely A, B, and C. Let us now write the interval notation for the intervals. For interval A, that is from negative infinity to 0. Interval B from 0 to 2. Interval C from 2 to positive infinity. Then step 3. We evaluate f prime of x using a test point for each of the intervals. Let's begin with interval A. Look at the A here. Let us take one integer closest to 0, and that is negative 1. So we evaluate f prime of negative 1. This is our derivative function. So we have now negative 6 times the square of negative 1 plus 12 times negative 1. The square of negative 1 is positive 1. And then 12 times negative 1 is negative 12. Now let us simplify further. Negative 6 times 1 is negative 6 minus 12, so we combine as negative 18. Interval B. Look at our interval B. Let us use the smallest integer in the interval B, and that is positive 1. So let's evaluate f prime of 1. So we have negative 6 times the square of 1 plus 12 times 1. 1 square is simply 1. 12 times 1 is 12. So negative 6 times 1 is negative 6 plus 12 is positive 6. Then interval C. Look at our interval C. Let us use a value that is the smallest integer in the interval C, and that is the positive 3. So we evaluate f prime of 3. So we have negative 6 times 3 square plus 12 times 3. 3 square is 9, and this 12 times 3 is 36. Now, negative 6 times 9 is negative 54 plus 36. So we have negative 18. Now let us identify whether increasing or decreasing on the interval. Look at our interval A. The value here is negative. So we say that it is decreasing on interval A. What about interval B? The value we got here is positive, and we say that it is increasing on interval B. What about interval C? The value we got here is negative. So we say that it is decreasing on interval C. Example 3. Use the first derivative test to find the intervals in which the function f of x equals x squared minus 6x is increasing or decreasing. Step 1. Let's find the critical points. We take the derivative of the given function. So we have f prime of x equals 2x minus 6. Then we let f prime of x equal 0. It means the left side of this equation is 0. Then let us solve for x. Negative 6 goes on the other side, so 6 equals 2x. Let us find the x by dividing this by 2. So the value of x equals 3. So we have one critical point for this problem. Step 2, let's identify the intervals. Let us draw the number line, and we assume the position of the critical point, and it's here. The number line is now divided into intervals a and b respectively. Let us now write the interval notations for a and b respectively. So we have for the a from negative infinity to 3. Interval b from 3 to positive infinity. Then step 3. We evaluate f prime of x using a test point for each of the interval. Let's begin with interval a. Notice that in a, the value 0 is there. So let's use that 0 for easy computation. So we have f prime of 0. That will be 2 times 0 minus 6. 2 times 0 is cancelled out. It is 0. So finally, the answer is minus 6. What about interval b? Let us take one value here. It is better to use the smallest integer for interval b. So that will be positive 4. Let's evaluate f prime of 4. So we have now 2 times 4 minus 6. 2 times 4 is 8. Then minus 6. Finally, the answer is positive 2. Let us now conclude whether increasing or decreasing for the interval. For interval a, the value is negative. So we say that it is decreasing on interval a. What about interval b? The value is positive value. So we say that it is increasing on interval b. Today we're going to study the second derivative test. Suppose f prime of x equals 0 and f double prime, or the second derivative, is continuous over an interval containing the point c. If the second derivative is greater than 0, or we say positive, then the function f has a local minimum at the point c. If the second derivative is less than 0, or we say negative, then the function f has a local maximum at the point c. If the second derivative of x is equal to 0, then the test is inconclusive. Let us see this example. Use the second derivative to find the location of all local extrema for the function f of x equals x raised to 5 minus 5x cubed. For our solution, the step 1 is to find critical points when f prime of x equals 0. This is our function here, so the first derivative will be 5x raised to 4 minus 15x squared. Let us set the first derivative into 0. So the left hand side will be 0 equals 5x raised to 4 minus 15x squared. Now, let us solve for x. Let us factor out the greatest common factor to each of the terms. So we have 0 equals the 5x squared times the quantity x squared minus 3. Now, let us equate each factor to 0. So we have the 5x squared equals 0, and this x squared minus 3 equals 0. Solving for x in the first equation, we have x equals 0. On the second equation, we can transpose this negative 3 to the right, and then let us take the square root of both sides, and the value of x is equal to plus or minus the square root of 3. We have now these critical points, and we say that the critical points are the values when x equals 0, square root of 3, and negative square root of 3. Step 2. Find the second derivative of the function and evaluate it using critical points of step 1. A while ago, we solved for the first derivative. Now, the second derivative is equal to 20x cubed minus 30x. We can simplify this expression into 10x times the quantity 2x squared minus 3. Now let us evaluate each of the critical points into the second derivative. Let's begin with the f double prime of 0. This is now equal to 10 times 0 times the quantity 2 times 0 squared minus 3. The 0 here outside makes the whole equation into 0. So the f double prime of 0 is equal to 0. Next, let us evaluate the f double prime of the square root of 3. This is equal to, we can simplify the radical and the power 2. So the number 3 here comes out as positive 3 to be multiplied to 2. So we have 6 minus 3. The difference will be 3, and that 3 will be multiplied to 10. So the f double prime of square root of 3 is equal to 30 square root of 3. Next, let us evaluate the f double prime of this negative square root of 3. This is now equal to 10 times negative square root of 3 times the quantity 2 times the square of negative square root of 3, then minus 3. We can simplify the expression here by cancelling the radical and the power 2. But take note, the negative sign here becomes positive. So when we cancel it out, the number 3 here comes out as positive 3 to be multiplied to the number 2. So we have 6 minus 3. And the difference is 3, and that 3 is to be multiplied with a 10. And everything now is simplified into negative 30 square root of 3. For step 3, let us now use the second derivative test. We say that if the second derivative is greater than 0 or positive, then the function f has a local minimum at the point C. Second, if the second derivative is less than 0 or negative, then f has a local maximum at the point C. But if the second derivative of the function equals 0, then the test is inconclusive, meaning there is no conclusion. Let us see now this f double prime of 0, and this is equal to 0. In this case, we say that it is inconclusive when x is equal to 0. Next is the second derivative of square root of 3, and the answer is positive 30 square root of 3. Since this is positive, we say that there is local minimum when x is equal to square root of 3. For the third critical point, and we have here the f double prime of negative square root of 3. And we found out that the answer is negative 30 square root of 3. Since this is negative, we say that there is local maximum when x equals negative square root of 3. Using the graphing facility, this is the graph of our f of x is equal to x power 5 minus 5x power 3. Let us examine the graph on its critical points. When x equals negative square root of 3, when x is equal to 0, and when x is equal to square root of 3. We say that there is local maximum when x is equal to negative square root of 3, and it's here. Also, there is local minimum when x is equal to square root of 3. This is the point. And then, there is no local extremum when x is equal to 0. This is the point. This is now our final answer. Example 2. Use the second derivative test to find the extreme values of the function y of x equals 4x cubed plus 21x squared plus 36x minus 20. Step 1. Let us find critical points. That is, we will take the derivative of the given function here. So, y prime of x equals derivative of 4x cubed is 12x squared. Derivative of 21x squared is 42x. Derivative of 36x is plus 36. Derivative of negative 20 is 0. Then we let y prime of x equal 0. For this equation, the left side becomes 0. And then let us simplify the right side. We can do factoring here. We can see that there is a common factor on the three terms of the right side. And that is positive 6. So this is 6 times the quantity 2x squared plus 7x plus 6. We simplify further the equation by dividing this equation by 6. If we do that, we can cancel the constant 6 here. And the left side, same 0 will come. So we have 0 equals 2x squared plus 7x plus 6. Then we factor out. The factors are 2x plus 3 times x plus 2 equals 0. We equate each factor to 0. So, 2x plus 3 equals 0, and the other x plus 2 equals 0. We solve for x. For the first factor equation, this positive 3, we transpose to the right, it becomes negative, then we divide by 2. So, x equals negative 3 over 2. The x plus 2 equals 0. The positive 2 we transpose to the right. So, x equals negative 2. These are the two values of critical points. Then step 2. Let us find the second derivative and evaluate using critical points. The first derivative is here, so let's begin taking the second derivative. Y double prime of x equals derivative of 12x squared is 24x. Derivative of 42x is plus 42. Derivative of 36 is 0. Now, let us evaluate the second derivative using the first critical point, the negative 3 over 2. So we substitute this value to the x. So it becomes 24 times the negative 3 over 2, then plus 42. We can cancel the 24 and 2, and this 24 becomes 12, multiplied by negative 3. So we have negative 36 plus 42. So the answer is 6, and this is positive. And we say that by second derivative tests, the function y of x has local minimum at x equals negative 3 over 2. What about second derivative with respect to the second critical point, the negative 2? So the function becomes 24 times negative 2 plus 42. 24 times negative 2 is negative 48 plus 42, we have negative 6. So the value is negative. By second derivative test, the function y of x has local maximum at x equals negative 2. Then we will go to step 3. I need to erase this part. I am going to copy the values of critical points here. Step 3 is evaluate the function f of x by local minimum and maximum respectively. Let's begin with minimum value. In our step 2, we say that the function has local minimum at the point x equals negative 3 over 2. So we're going to use this value to get the minimum value here. So y of negative 3 over 2. This is our function. So this function becomes like this. We change all the x by the value negative 3 over 2. Then let us simplify. The cube of negative 3 over 2 is negative 27 over 8. The square of negative 3 over 2 is positive 9 over 4. This negative 3 halves times 36, we will get negative 54. Then we simplify further. This 4 times this fraction will give us negative 13.5. 21 times 9 over 4 is 47.25. Then we copy negative 54 minus 20. Simplifying further, the final answer here is negative 40.25. Let us copy this value in here. Let's proceed with maximum value. From step 2, we say that the function has local maximum at the point x equals negative 2. So we will use this negative 2 to find the maximum value. That is y of negative 2. Our function given here becomes like this. We change all x by the value negative 2. Then let us simplify. The cube of negative 2 is negative 8. Times 4 is negative 32. The square of negative 2 is positive 4 times 21 is plus 84. 36 times negative 2 is negative 72. Then we copy the negative 20. When we simplify, final answer is negative 40. We copy this value in here. These are the final answers. Example 3. Use the second derivative test to find the extreme values of the function y of x equals negative x cubed plus 3 over 2 x squared plus 18x. Step 1 is to find the critical points, meaning first step is to get derivative of the given function. Y prime of x equals negative 3x squared plus 2 times 3 over 2x plus 18. So this is the derivative of the given function. let us simplify further. We can cancel these two with the denominator. So finally, y prime of x equals negative 3x squared plus 3x plus 18. Then we let y prime of x equals 0, meaning the left side becomes 0 and we simplify. We can do factoring here by removing a common factor. The trinomial has a common factor, and that is negative 3. And it becomes like this: negative 3 times the quantity x squared minus x minus 6. We can remove that constant negative 3 by dividing this equation by that same value. When we do that, we can cancel this negative 3 and the left side will just be 0. So x squared minus x minus 6 equals 0. We can factor this out. Factors are x minus 3 times x plus 2 equals 0. We equate each factor now to 0. So we have x minus 3 equals 0 and x plus 2 equals 0. Then we solve for x. In the first factor equation, negative 3 is transposed to the right. So x equals positive 3. On the second factor equation, this plus 2 we transpose to the right. So we have x equals negative 2. These are the critical points. Then we go to step 2. Let's find the second derivative and evaluate using critical points. Our first derivative function is here. Therefore, the second derivative equals derivative of negative 3x squared is negative 6x. Derivative of 3x is plus 3. Derivative of 18 is 0, so we don't write here. Let us now evaluate the second derivative using the first critical point. So we have y double prime of 3. This is our function. So it becomes negative 6 times 3, then plus 3. The product, negative 6 and 3, will be negative 18, then plus 3. So we have negative 15. So we have a negative value here. By second derivative test, the function y of x has local maximum at x equals 3. Then the second critical point. So we have y double prime of negative 2. So this function becomes negative 6 times negative 2, then plus 3. The product, negative 6 and negative 2, is positive 12, then plus 3. So we have positive 15. We have a positive value here. By second derivative test, the function y of x has local minimum at x equals negative 2. Now we go to step 3. I need the space here. First, I'm going to copy the critical points value, and it's here now. Then step 3, we evaluate the function f of x by local minimum and maximum respectively. Let's begin with maximum value. In our step 2, we said that there is a local maximum at the value x equals 3. So we evaluate our function with that value 3. So we have here y of 3. This is our function. So it becomes like this. We change all x by 3. Then we simplify. 3 cubed, and there is a negative sign outside, is negative 27. Plus 3 squared is 9, times 3 is 27, divided by 2 is plus 13.5. Plus 18 times 3 is 54. Finally, the answer here is 40.5. This is our maximum value. We copy it somewhere here. Then we go to the minimum value. In our step 2, we said that the function has local minimum at x equals negative 2. So this value of negative 2 we're going to use, and that will be y of negative 2. We evaluate this given function, and it becomes like this. We change all x by negative 2. Then we simplify. The cube of negative 2, we write here negative 8. Still the negative sign here is copied below. Then plus. The square of negative 2 is positive 4. Then the product 18 and negative 2 is negative 36. We simplify further. Negative and negative becomes positive 8. 3 times 4 divided by 2 is 6. And we copy the negative 36. And when we simplify, the final answer is negative 22. This is our minimum value. Today we're going to study concavity and points of inflection. Let us define first concavity. Let f be a function that is differentiable over an open interval I. If f prime, or we say if the derivative is increasing over the interval I, we say the function f is concave up over the interval I. If f prime is decreasing over the interval I, we say f is concave down over the interval I. I have here one graph over the interval from A to B. On the graph, there are examples of two tangent lines given in dotted lines. This is the first tangent line. This is the second tangent line. Looking at the graph from left to right, we can observe that the slopes of the tangent lines are increasing. Thereby, we say that the derivative is increasing over the interval from A to B. In that case, the function f is concave up. Another example is this graph over the interval from A to B. On the graph, we have two tangent lines again. This is the first tangent line. Here is the second tangent line. Looking at the graph from left to right, we can observe that the slopes of the tangent lines are increasing. In that case, we say also that the derivative is increasing over the interval from A to B. In that case, the function f is concave up. Third example is this graph over the interval from A to B. In here, we have two tangent lines. This is the first. Here is the second. Looking at the graph from left to right, the slopes of the tangent lines are decreasing. In that case, we say that the derivative is decreasing over the interval from A to B. We know that if f prime is decreasing over the interval, we say that the function is concave down over the interval from A to B. This is our fourth graph over the interval from A to B. On the graph, we have two tangent lines. This is the first tangent line. This is the second tangent line. Looking at the graph from left to right, we can observe that the slopes of the tangent lines are decreasing. So we say that the derivative is decreasing over the interval from A to B. In that case, if f prime is decreasing over the interval, we say also that f is concave down. There is a note. If the derivative is constant, then the graph of f is said to have no concavity. Let us now define point of inflection. If the function f is continuous at the point A and f changes concavity at the point A, the point A, f of A is an inflection point of the function f. Here I have a graph, and on this graph we have 6 tangent lines. This is the first, second, third, fourth, fifth, and sixth. When x is equal to A, we have this point of the graph. Let us observe that the part of the graph on the left side of A, we're going to look at the graph from left to right, and we can see that the slope is increasing. Meanwhile, the part of the graph on the right side of A, please observe that the slope here is decreasing. Now this point with coordinates A, f of A is what we call the inflection point, because this is the point where the function changes concavity. A while ago, we say that on this interval here, the slope is increasing or the derivative is increasing. So this is a picture of the function which is concave up on this interval. While the right side of A, we notice that the slope or the derivative is decreasing. So on this interval, that the function is concave down. There is a note. Inflection point occurs when the second derivative of x is equal to 0, or if the second derivative of x is undefined. Let us go now to the test for concavity. Let f be a function that is twice differentiable over an interval I. If f double prime of x is greater than 0, or we say that if the second derivative of the function is positive for all x, an element of the interval I, then the function f is concave up over the interval I. Second, if f double prime of x is less than 0, or we say that if the second derivative of the function is negative for all x, an element of the interval I, then the function f is concave down over the interval I. Today, we're going to find points of inflection and intervals of concavity. Here are the steps to find points of inflection and intervals of concavity. Step 1. Find the second derivative of the function x. Step 2. Find the inflection points. Inflection point occurs when f double prime of x equals 0 or f double prime of x is undefined. For the first case, when f double prime of x equals 0, we can do this by setting the f double prime of x equals 0 and solve for x. the resulting value of x is the inflection point. Letter B, when the second derivative is rational, or we say a fraction, set the denominator to 0 and solve for x. The resulting value of x is the inflection point, and that is the point when the second derivative is undefined. Step 3. Divide the interval into sub-intervals using inflection points as endpoints. Step 4. Choose an arbitrary test point on each sub-intervals and evaluate the second derivative of the function on those test points. Step 5. Test for concavity. We say that if the second derivative of the function is greater than 0, or we say positive, then the function is concave up over that subinterval. If the second derivative of the function is negative, or we say less than 0, then the function is concave down over that subinterval. Let us see this example. For the function f of x equals x cubed minus 6x squared plus 9x plus 30, determine all intervals where f is concave up or concave down. List all inflection points for the function f. For our solution, let us do step 1, that is to find the second derivative of the function. The function is here, so the first derivative will be f prime of x equals 3x squared minus 12x plus 9. Therefore, the second derivative will be 6x minus 12. Let us copy our second derivative below step 1. Step 2 is to find the inflection points. We say that inflection point occurs when f double prime of x equals 0 or f double prime of x is undefined. Observing our second derivative here, this is a polynomial function. So it means this is defined in all its domain. Thus, it falls on the first case only. So we set the f double prime of x equals 0 and solve for x. So we have now 0 equals 6x minus 12. Let us now solve for x. This negative 12 we will transpose to the left side. It becomes positive 12 equals 6x. Let us divide this equation by the coefficient of x, which is 6. So we have here 12 over 6 is equal to 2. So the value of x equals 2. This is our inflection point. And we say that inflection point occurs when x is equal to 2. Step 3. Divide the interval into sub-intervals using inflection points as endpoints. Initially, the interval is all real numbers. So first, let us write our x-axis, and we put the number 2 being the inflection point in the middle. In this problem, there is only one inflection point. Now, let us identify the corresponding sub-intervals. On the left side of 2, the sub-interval is from negative infinity to positive 2. while on the right side of this number 2, the subinterval is from 2 to positive infinity. Now, we have the step 4, and that is to choose an arbitrary test point on each subintervals and evaluate the second derivative of the function on those test points. On this interval, we may choose the number 0 for easy computation, while on the other interval, we may choose the first integer after 2, and that is the number 3. Now, let us evaluate the second derivative on those test points for the 0 and the number 3. The second derivative is here. Let's begin with f double prime of 0. This is equal to 6 times 0 minus 12. And the answer here is simplified into negative 12. Next is f double prime of 3. And this is equal to 6 times 3 minus 12. 6 times 3 is 18, minus 12 is positive 6. Now step 5. Let us test for concavity. We say that if the second derivative is positive, then the function is concave up over that subinterval. Also, if the second derivative is less than 0 or say negative, then f is concave down over that subinterval. So look at our f double prime of 0, the answer is negative 12. Because this is negative, we say that on this subinterval, the function is concave down. While the second derivative with respect to number 3, the answer is positive 6. Because this is positive, we can conclude that on this subinterval, the function is concave up. From step 2 a while ago, we found out that the inflection point occurs when x is equal to 2. So the point is 2, f of 2. We want to get the actual value of this f of 2. So let us evaluate the function with respect to 2. So we have f of 2 equals 2 cubed minus 6 times 2 square plus 9 times 2 plus 30. We can simplify 2 cubed into 8 minus the 6 times 2 square is 24 plus 9 times 2 is 18 and then plus 30. When we simplify the numbers here, the answer is 32. So the coordinates of our inflection point is 2, 32. Let us take a note of this inflection point in here. Now using our graphing facility, this is the graph of our function. We can see that the point 2, 32 is the inflection point. Look now on the subinterval on the left side of 2. You can see that the function here is concave down, while the subinterval on the right side of 2, we can see that the graph is concave up. This is our final answer. Example 2. For the function y of x equals 2x cubed minus 3x squared, determine all intervals where f is concave up or concave down. List all inflection points for f. the step 1 is, let us find the second derivative. Of course, we should come first to the first derivative, and that is 2x cubed is now 6x squared, minus the 3x squared is here 6x. So the first derivative is 6x squared minus 6x. Then the second derivative, we have now 12x minus 6. Step 2, let us find the inflection point or points. We set the second derivative equals 0 and solve for x. So this 12x minus 6 equals 0. Let us now solve for x. We can do like this. The negative 6 we transpose to the right. So we have 12x equals positive 6. Then x is equal to 6 over 12. Or this is simplified into 1/2. We have one inflection point at x equals 1/2. Step 3. Let us draw the intervals using inflection point. In the number line, we put the inflection point in the middle, and we can see that the number line is divided into two intervals. We identify the interval here to be the negative infinity, comma, 1/2. On the right side, the interval is 1/2, comma, infinity. Step 4. Let us now evaluate the second derivative on test point for each interval. A while ago, we listed the second derivative, that is 12x minus 6. Now let us identify the test point for each of the interval. In the interval here, since 0 is part of this interval, we use the 0. On the right side, in this interval, we use the smallest integer, and that is 1. So for the first interval, we have y double prime of 0. This is equal to 12 times 0 minus 6. This 12 times 0 is 0, so the answer here is minus 6. For the second interval, the test point is 1. So we have y double prime of 1. And then we have 12 times 1 minus 6. 12 times 1 is 12, minus 6 is 6. For step 5, we know the test for concavity. If the second derivative is more than 0 or positive, then f is concave up over that interval. If the second derivative is negative or less than 0, then f is concave down over that interval. So we can see here in the first interval, the value is negative. That means in here, it is concave down. For the second interval, the value 6 is positive. That means it is concave up on this interval. Now from step 2, we learned that inflection point as x equals 1/2. We can see this also in our illustration here. Now let us solve for the y value of the inflection point. That is, we evaluate the function by the inflection point to get the y. So we have y of 1/2 equals 2 times cube of 1/2 minus 3 times square of 1/2. This cube of 1/2 is 1 over 8. The square is 1/2 is 1 over 4. We can simplify these two by 1 over 8. That will be 1 over 4 minus, while the second expression here becomes 3 over 4. So 1 over 4 minus 3 over 4 is negative 2 over 4, which we can simplify further into negative 1/2. That means the inflection point has coordinates 1/2, comma, negative 1/2. Example 3. For the function f of x equals x raised to 4 plus x raised to 3, determine all intervals where f is concave up or concave down. List all inflection points for f. Step 1, let us find the second derivative. We start with the first derivative, and that is 4x cubed plus 3x squared. Then the second derivative, we have 12x squared plus 6x. Step 2, let us find the inflection point. We set the second derivative equals 0 and solve for x. So we equate here the 0, and then let us solve for this by factoring. There are two terms here, and there is common. And that common, we factor it out. So we have 6x times the factor 2x plus 1 equals 0. There are two factors for our second derivative. So we equate each factor into 0 and solve for x. So we have 6x equals 0, and this 2x plus 1 equals 0. Let us solve for x here. So the x equals 0 over 6 or 0. 0 is the first inflection point, while here the positive 1 we transpose to the right, becomes negative 1. Then we divide by 2. X now equals negative 1/2. There are two inflection points at x equals 0 and x equals negative 1/2. Then step 3, let us draw the intervals using the inflection points. In our number line, here are the two inflection points, the negative 1/2 and the 0. The number line here is now divided into three intervals. Namely, here is the negative infinity, comma, negative 1/2. In the middle, negative 1/2, comma, 0. And on the right, we have 0, comma, infinity. Step 4, we evaluate the second derivative on test point for each interval. We have the second derivative written here. For the test point, for the first interval, we use negative 1. For the second interval, we will use negative 1 over 4. On the third interval, we will use 1. Let's begin with the first interval, so that is f double prime of negative 1. So we have 12 times the square of negative 1 plus 6 times negative 1. We have positive 6. For second interval, we will use the test point negative 1/4. So f double prime of negative 1 over 4. So we have 12 times the square of negative 1 over 4 plus 6 times the negative of 1 over 4. We simplify this square of negative 1 over 4, we get positive 1 over 16 minus 6 times 1, this will be 6 all over 4. Note that this 12 over 16 we can simplify as 3 over 4, then minus 6 over 4. And the answer here is negative 3 over 4. For third interval, our test point is positive 1. So we have f double prime of positive 1. We get 12 times 1 square plus 6 times 1. Square of 1 is 1 times 12. So we get 12 plus 6. The answer here is 18. For the test for concavity, if second derivative is positive, then concave up. If second derivative is negative, then f is concave down on that interval. Look at the first interval here. The value is 6, positive. That means it is concave up on the first interval. For the second interval, the sign is negative. That means it is concave down on this interval. For the third interval, the value is positive 18. Since it is positive, again, this interval is concave up. Now, for the inflection points, we have two values for the x, negative 1/2 and x equals 0, as we can see here also in our illustration. We want to get the y value for each of the points. We are going to evaluate the function using these points. Let's begin with the first value, the negative 1/2. So that will be f of negative 1/2. We have fourth power of negative 1/2 plus third power of negative 1/2. Simplifying, fourth power of negative 1/2 will give positive 1/16 minus the third power of negative 1/2 is 1/8. The minus sign is here. Then we simplify this into negative 1/16. That means the coordinates for the first inflection point is negative 1/2, comma, negative 1/16. For the second, we evaluate f of 0. So we have 0 power 4 plus 0 power 3. This is 0 plus 0. Ultimately, we have 0. That means for the second inflection point, the coordinates are 0, 0. This is the origin.